And so we get to the infamous cross product or vector product. What is it? Well, first of all, I understand why the textbook that I'm shadowing as I make these videos is Young and Friedman's University Physics. And they put this cross product at the very end of Chapter 1. I understand a little bit why they do that, because they want to get all the introduction stuff out of the way. But really, you don't need to know this at the beginning of a physics course. The cross product doesn't come into play until much later in a course, in particular when you get into torque, or the force it takes to turn something like a screwdriver. And then you get it maybe even in second semester or third semester physics, when you get into electricity and magnetism, and you're talking about the force on a charge moving through a magnetic field. The cross product comes into play there too. That's like chapter 22 in university physics. So you don't really need to know the cross product at the beginning of a physics course unless you have a professor who particularly likes to torture you, which is unfortunately sometimes the case. So what is the cross product of two vectors? Let me do a little review. First of all, what is a vector? A vector is a magnitude with a direction. So recently I went to a wedding, and the church where the wedding was is about 3 miles due south of where I'm sitting right now. That's a vector. It has a magnitude, 3 miles, and it has a direction, due south. Ta-da! That's a vector. Now, a vector doesn't have to be distance. It could be a velocity in a certain direction, or it can be an acceleration in a certain direction, or a force in a certain direction, and so forth. Now, you can add vectors together, and I have a video on that. So to get to this church, you might have gone such and such a distance south, and then such and such a distance west, and then such and such a distance south, and then such and such a distance east, and then such and such a distance south again. If you add up all those individual vectors by lining up the heads to the tails, to the heads to the tails, to the heads to the tails, to the heads to the tails, guess what the sum of all of those vectors added together will end up being? It will end up being 3 miles due south of where I'm sitting now. So that resultant, 3 miles due south, magnitude with direction, is the sum or resultant of all those different vectors added together. That's vector addition. You can also subtract vectors too. So, in another video, I talked about what's called the dot product. This video is about the vector product. By vector product, I mean a way of multiplying two vectors together that ends up being a vector, that is a magnitude with direction, as your product. There is also a dot product where you multiply two vectors together and you end up with a amount, a quantity, without a direction. That's the scalar or dot product of two vectors. A scalar is a magnitude without direction. So we can say speed is a scalar. If you think he just ran 3 miles per hour, that's a speed, but I haven't told you what direction. That's a scalar. A vector would be to say he ran 3 miles per hour in due east. That would be a vector because it has direction. By the way, I suppose by definition that's not running. It's not fast enough. But that's not important right now. So just to review what the dot product is, let me go to the bottom here. The dot product is the magnitude that results when you multiply a vector by the part of another vector that is going in the same direction. That's what the dot product is. The dot product is the magnitude of multiplying two vectors together, where you pick either of the vectors. Doesn't matter which one you pick. It is the multiplication of a vector times the part of the other vector that's going in the same direction. And the way that ends up when you build triangles and use trigonometry, that basically ends up by saying that the dot product of vector A and vector B is AB cosine theta, where theta is the angle in between the two vectors. So the reason this works is because A cosine theta is the part of A that's going in the same direction as B, and B cosine theta is the part of B that's going in the same direction as A. I don't want to spend time explaining it because I did a whole other video on it and I haven't even gotten to the cross product yet. But that is a review of vector addition and vector multiplication thus far. This video is about the cross product. Unlike the dot product, the cross product is the first vector when you're multiplying two vectors. So to do the order you do it matters with the cross product. The order you do it doesn't matter with the dot product, but with the cross product, you start with the first vector. So if you have A cross B, you start with A. The cross product is the first vector times the part of the other vector going not in the same direction, like the dot product, but the part of the other vector going in the perpendicular direction to the first vector and pointing in the third dimension. So the direction of a cross product is going to be coming into or out of the direction of the plane that those two first vectors are in. It's going to be a third dimensional thing, the cross product. And this just works. It does. I've kind of waited to make this video until I felt like I understood it as much as I could. Hopefully I'll understand it even more. But this works in certain areas. It works with torque, with wrenches, and it works with screwdrivers, and it works with wrenches too, and it works with electromagnetism. But basically, the cross product is going to be a third dimensional vector based upon taking the first vector and multiplying by it the perpendicular to that other vector. Now, what does this end up looking like? What are we talking about here? Well, first of all, what does it look like? First, as I said, the order in which you multiply the vectors does actually matter. So with the dot product, vector A dot B is the same as vector B dot A. But with the cross product, the direction does matter. The cross product of vector A and vector B is not exactly the same as the cross product of B cross A, but it's going to be the opposite, the negative B cross A. So the order you do it matters. So the commutative property does not work for cross products. And go remind yourself what commutative is. If you understood what I said, you don't need to know the label for it. Secondly, how do you picture it? So if we're doing the cross product of vector A cross B, then instead of the cosine of theta, where theta is the angle between them, it's going to be A times the sine B sine theta, the perpendicular to B to A. Again, this just works. It works with torque. So, for example, the force cross the perpendicular to where the axis of turning is going to be, that this works to figure out the torque. I don't know why it works. I'm trying to work on that, but it does. So the A cross B is going to be the magnitudes AB times the sine of the angle between them. So that's what we mean when we talk about the perpendicular. And then how do we figure out which direction it's going at in the third dimension? We're going to use something called the right-hand rule. So we could have picked the left hand, but we picked the right hand. Physicists have. So you're going to figure out. So if it's A cross B, you put. Let's go back. If it's A cross B, you're going to use your right hand, and you're going to start. And this may be looking opposite in the video, by the way, of the way it is. So there's a mirror dynamic here to the videoing. But as I'm looking at it, so probably for you, if I'm getting it right, and in my video, if you're looking at the video, I start with A and wrap around to B with my right hand, and so the vector would be pointing out of the video. You would do it the opposite with your the mirror effect, I think. So anyway, that's what we talk about by the right-hand rule. We're going to start with A with our right hand, and we're going to curl around toward B, and that's going to point us in the direction of the cross product. Okay, so what if we're doing the cross product with X, Y, and Z components? Well, now it gets really tricky. If you've understood what I've said so far, you might want to take a breather and watch this some other day, because now is where it gets really difficult. So let's say you want to do A cross B, and you have the components, AX, AY, AZ, and BX, BY, BZ. AX, AY, AZ being the components of vector A, BX, BY, BZ being the components of vector B. What is this IJK stuff I've got there? Well, in a previous video I talk about unit vectors. I usually means X, J usually means Y, K usually means Z. So basically this is just it's not a true multiplication in a way. It's just saying it's going in the X direction for I, going in the Y direction for J, and going in the K direction for Z. So now, and if you read this section in Young and Friedman, they just multiply all this out: AXI times BXI, AXI times BYJ, AXI times BZK, and they add all that up, and it's a whole lot of stuff. Now the good news is that when you do the cross product of two I's or two J's or two K's, it becomes 0, because if the sign between two things is part of the multiplication, well, the sign of 0 is 0, and so that just, all of the I's times I's and all of the J's times J's and all of the K's times K's all disappear from that long list of things. And so what we end up with is, if we collect our terms, is that the cross product of these components ends up AYBZ minus AZBY. That's going in the X direction. And then AZBX minus AxBz, that's going in the Y direction. And then AxBy minus AYBZ going in the Z direction. Now, this is something you don't necessarily have to memorize. You can just come back to the book at this point. If a professor at some point gives you a problem where you have to figure out the cross product using components, just look up this formula and you'll be fine. And that's the ticket. So C, if C is the cross product at the end, then it's going to be CX is going to be AYBZ minus AZBY, and CY is going to be AZBX minus AxBz, and CZ is going to be AxBy minus AYBX. Okay? Again, you don't necessarily have to memorize this, just know where to look it up when you're given that sort of a problem. Now, if you do happen to know determinants, if you do happen to know matrix algebra, and most Algebra 2 classes at least spend a day or two on determinants, you can express what I just said in determinant form if you lay it out like this. So if you have the unit vectors as the top row, I, J, and K, and then you lay out AX, AYZ, BXYZ, if you lay it out like this, you can actually get the same thing using determinants. How do you do determinants? One way to do it with a 3x3, this is called a 3x3 determinant. If you take the I and the J row and you copy it at the end, so you recopy it at the end, then you can do crosses to get it. But another way you might think of it is when you're crossing the I's, you eliminate this first row and then go AYBZ, AZBY. So you do AYBZ going crosswise down at the bottom minus AZBY. So that gives you the first component. And then if for the second component, if you eliminate the J, it's going to be AxBz minus AZBX. And then for the K, if you eliminate the K row, it's going to be AxBy minus AYBX. That's going to give you the same thing as the bottom one. So if the professor isn't going to let you look up this formula, then if you remember to set it up like this and you know how to block out each row, then you can come up with that formula again. Well, I know cross products aren't particularly easy, but you can handle it, especially when you actually get to it in a book.